All right, so using racial estimator, we can estimate the population mean. Similarly, we can use the racial estimator to estimate the population total. Back to the orange example, we can use our sample R, which is the estimated R that is defined as the Y bar divided by X bar from our sample. We use our R to multiply to the tau X, then we can obtain or estimate the tau Y. Taking the variance on both sides of these equations, since tau X is a constant, so variance of it becomes a tau X squared, multiplying the variance of R. Variance of R is divided as 1 over X bar squared multiplied to final population correction factor times SR squared over N. Tau X squared could be expanded like capital N times capital X bar. So the X bar square could be cancelled out, leaving N squared multiplied to this term. And this term is actually equals to the estimated variance of Y bar from the racial estimator. Next, we can determine the sample size under the racial estimation. We can set out our bound of error and also the significance level alpha. Then we can come down to the formula of determining the sample size. Sample size is given by 3.30 equations as NSR squared divided by N times D squared plus SR squared. But beware, when we are trying to look at the racial estimation, if we are using SR squared, then there would be a mu X squared inside the D squared. Okay, I'm not going through each of the steps to prove this equation, but you're welcome to do so. Next, we want to ask, comparing the racial estimator with the ordinary estimator of the Y bar, which is the summation of Yi divided by N. We want to compare which estimator is better than the other. Simply, we look at the variance estimate. Let's look at the ordinary method. The estimated variance of Y bar equals to the final population correction factor multiplied SY squared over N. Under the racial estimator, that is multiplying to SR squared. SR squared could be expanded to SY squared minus 2R SXY plus R squared SX squared. So with the racial estimator, the variance estimate not only depends on the variance of Y in our sample, it also depends on the variance of X and also the covariance part of the variable X and Y. So which one is better than the other? Let's use A subtract B. If A subtract B is greater or equal to 0, that means the A is greater than B, right? So equation 1 minus equation 2. The common factor SY squared multiplied to the factor would be gone. So we won't see SY squared. With the subtraction, after we subtract into 2, we would end up having this bit 2R SXY minus R squared SX squared multiplied to a factor. And this factor will always greater than 0, so we can ignore that. Having this part greater or equal to 0, then we're trying to find that the racial estimator uses smaller variance. Okay, so when would that be happening? So with this factor greater or equal to 0, so move R squared SX squared to one side and R SX squared less than or equals to 2SXY. Further, if we let the variance, taking square root, SY divided by Y bar, it is called the coefficients of variance. Coefficients of variance measure the variance, standardizer variance, because it's measured the SY, the variance, or the standard deviation, divided by the mean value. and Cx is Sx divided by x bar. Correlation between x and y equals to Sxy divided by Sx divided by Sy. Okay, so we want this term greater or equal to 0. Then we move 1 on the other side and play around, having r on one side and Sx squared, put it into the denominator. Sxy divided by Sx squared is equals to rho times Sx over Sx. Okay. Now, with this bit, we can also have r equals to y bar divided by x bar. The purpose of having that is that we would have sy divided by y bar, and then we would have sx divided by x bar. Okay, play around. We're trying to find that as long as the correlation between x and y variables is greater than 1/2 times the cx divided by cy, then the ratio estimator would be better than the ordinary estimator. Or in other words, if rho is greater or equal to 1/2 cx divided by cy, implies that the ratio estimator has a smaller variance. If the ZV of the x, coefficients of variance of x, exceeds twice the coefficients of variance of y, then the ratio estimator would have a larger variance. That's the other way to put it. Okay? At last, I would say if you pay attention to the proof or the ratio estimator, I would only put ratio estimator is not always true. That means the expected value of our ratio estimator is not always being an unbiased estimator for the population R. Why? And how can we find a better estimator? You can think about that. We can discuss about that on Friday.